So today, we are talking about quantum computers, a potential breakthrough technology that may have virtually unlimited applications, much like normal computers. Unfortunately, like a lot of technology, especially anything with the word quantum in it, quantum computing has picked up a lot of myth and not a lot of clear explanation. This is always our problem with quantum. It is not a very common sense or intuitive area of study, and this confusion gets exacerbated a lot by both the terminology and the tendency of quantum to attract both bad explanations from folks who don't understand it as well as they should to be explaining it, and the sheer amount of philosophical and mystical ponderings that it tends to inspire. If you have read or watched any explanations of quantum computing or quantum entanglement before, you will probably have heard the term superposition, for instance. It is vitally important to explaining the concept, but the term itself is usually not well explained. Quantum, for instance, was a regular word variation of the word quantity until about a century ago. A quantum, or quanta, is just a piece of something, a quantity. Measuring very tiny quantities of energy, of light for instance, which acts a lot like a wave normally, made us start noticing that light came in discrete and specific packages, or quanta, which we eventually determined were photons, particles of light with a size and energy content specific to their color. The weird paradox between the wave-like quality of light and these particle quantums of light led to the field of quantum mechanics. And almost nobody uses the term quanta for anything else anymore, so the term now seems a bit obscure when it was never intended to be. The same thing for quantum entanglement. Two or more particles can get themselves tangled together, which is to say what happens to one affects the other. Entangling two particles is pretty straightforward. Keeping many of them all entangled with each other and in a way we can look at is way harder. It is, however, necessary for quantum computing. The more particles you have entangled together, the more computing you can do, and it rises exponentially, so double the number of entangled particles does a lot more than double your computing power. Now, superposition is both a bit trickier and easier to explain. For the most part, it just means several things sharing the same spot or position, usually waves, and in quantum, everything is a wave unless you are actually looking at it at the moment. Quantum isn't weird because of what it discusses, that just seems arcane because of the math. What is weird about quantum is that all the randomness and uncertainty appears to be real, not just us not knowing. For instance, there is nothing weird about being told that inside a closed box is a cat who may or may not be dead, and you won't know until you open it. I can't remember most of what is in my desk drawers, let alone where each item is in that drawer. But I know that everything is in the spot I last left it, and if it's not there, there's a reason. Stuff got shaken around when I closed or opened it, for instance. I could build up a mathematical model of what is likely to be in those drawers, or somebody else's desk I was peeking around in, and what the percentages are of, say, an unsharpened pencil, a paperclip, and so on. The weird thing about quantum is that when I shut that drawer, everything is genuinely existing in a weird and actual haze of uncertainty until I open the drawer back up and absorb the contents, in which case everything settles back into one spot. I abhor the dead cat analogy of Schrödinger's thought experiment, and it was just a thought experiment. It works just as well with, say, a hungry and a fed cat. He did actually have a cat, incidentally, named Milton if you're curious, but there's no indication he would ever have tried to perform the actual experiment. But in the classic example of the cat in the box, you can't just substitute the vial of poison for a tin of cat food that is opened by a particle decay. Same scenario, but instead of the cat being simultaneously alive and dead, you instead just have a fed and sleeping cat or a hungry and irritable cat. In real life, I can't tell which cat exists, at least if the box is truly closed off from the outside world till you open it. In reality, cats are often fairly noisy in boxes, and hearing what is going on is the same as opening the lid and looking inside. If I don't know which, I have to assume either could be true, that the box has two realities superimposed on each other, in superposition, until I open the box and collapse the probability to 0% for one option and 100% for the other. Again, the only weird thing about quantum is that my uncertainty isn't just ignorance of what's going on inside, but the implication that we genuinely have two different coexisting states of existence in superposition till I look and actually collapse one of those states to 0% and raise the other to 100%. For the quantum entanglement option, we can treat our cat as a particle. Let's say we have two boxes sitting next to each other, and each has a tin of cat food with a particle detector on it. It will open one can or the other randomly when I shut both lids. It can be either one, but just one. So I put one cat, Milton, into one box, and in the other I stick another cat. We will say Prospero, one of my own cats and the one sitting on my desk at the moment as I write this. When I shut both lids, a particle spits out and can go left or right. If it goes one way, it opens up one lid, and the other for the other way. So there is a 50-50 chance of either can opening, but in doing so the other can't open. Incidentally, this doesn't have to be 50-50. We could arrange our experiment so there was a 90% chance of the can on the left opening, and only 10% for the can on the right, and the same number of possible states exist, just the odds change. With just one cat, we only have two states. That cat is fed or hungry. Now we have two cats who could be either fed or hungry, but their states are entangled. If one is fed, the other is still hungry. So we can't have two fed cats or two hungry cats. So we will still only have two possible states of existence. Milton and Prospero are entangled. Now, even if I pick up one box and carry it into another room, they are still entangled. I could transport Prospero's box to the other side of the solar system and open it, see him sleeping contentedly inside after eating, and know instantly that Milton is back on Earth in his box, angrily waiting on dinner. This is that spooky action at a distance we often talk about in quantum, because this information goes faster than light. And again, there's nothing weird about that knowledge. If I stick a letter in one envelope and nothing in another, and mail both to different addresses without looking at which address got sent which letter, I know which one had the letter at it the moment I check either envelope. Doesn't matter if the other letter was mailed to the Andromeda Galaxy. It's only spooky in the quantum case because all indications are that those two possible states were both actually going on until we looked inside, not just probabilities whose uncertainty was simply because we personally did not know. Also, by the way, I could have made 4 states instead of just 2. Instead of allowing my random quantum particle to go left or right and trigger food for either Milton or Prospero, I could have let it go up or down too, and for up it releases a catnip-covered toy to Prospero, and on down to Milton instead. Now I'd have 4 equally likely states, all simultaneously existing or in superposition. And I could skew those odds by setting up the sensors so up or down will each only say 10% likely to occur, and left and right each 40% instead of 25%. Nothing has changed but the probabilities. I could set it up so it was 97% likely to give Milton the toy, and only 1% for each other option, same results. Now I could also entangle 3 cats. I could set up another box and drop my cat Link in there. Going back to my original experiment, Milton or Prospero gets fed, we could rig things up so if Milton got fed, Link got fed too, and if Prospero got fed, Link got the catnip toy instead. Now all 3 of them are entangled. By absorbing the contents of any box, I know what happened in the other 2 boxes. In classic computing, we could say each of those boxes contained information, hungry or fed, 0 or 1, a single bit of data. In quantum computing, we have a qubit instead, or a quantum bit. The term qubit dates back to a 1983 paper on the concept of quantum money by Stephen Weisner, though it was coined by Ben Schumacher. He liked its similar sound to the cubit, the length of measure of about half a meter commonly used in the Bible. The qubit is the basis of quantum computing, much as the bit is for classical computing, and just as 8 bits makes a byte, 8 qubits makes a qubit. But whereas a bit can be only 0 or 1, a qubit can be a 0, a 1, or anywhere in between that. A classic byte, as 8 bits, can be any of 2 to the 8th or 256 possible permutations. Typically this is our smallest actual bit of addressable memory, because it can be one character, a number or a letter or a symbol. So hypothetically you could store any letter, number, or symbol on a byte, but on a qubit, you could in theory be storing all 256 of them at once. Of course, when you go to look at that qubit, it would collapse states to one specific letter, and presumably a random one, which would seem to make it not very useful. What's useful is on the calculation side. A classic computer uses bits and logic gates to do calculations. A quantum computer using quantum logic gates does that too. But while the classic computer will perform one calculation off that one set of digits, the quantum one is going to calculate those digits too, all of them. Hard to picture if you're not too familiar with core concepts of computing, so let's use our box analogy, only this time it's a room, not a box, and I stick a person inside it. And what our quantum random objects is going to be is two numbers, each between 0 and 9, each selected randomly. And I tell that person that when they see those, they are to multiply them up. I close the door and hit the quantum switch, and two numbers pop up. We now have 100 states. One where the person saw two zeros and got 0, one where it was a 1 and a 0 and they got 0, one where it was a 0 and a 1 and they got the same, and so on, all the way up to 9 times 9 equal 81. 100 simultaneous states and calculations all going on in that room, until I open the box and 99 of those states collapse, leaving one state that remains, 6 times 7 equals 42. Now how would that be useful? I'm going to stretch the science here a bit to make it intuitive. Real-world analogies for quantum are always a bit iffy. So imagine if I told that person that if they got 42 as an answer, they should open the door and step outside. There's only two people who can come walking out that door, the one who got 6 times 7 and the one who got 7 times 6. Now imagine I had a spreadsheet that had two columns, name and phone number, thousands of names and numbers, but somebody jumbled the sheet. Names are no longer linked to numbers. I've still got a phone book, but it is a hard copy, not digital. I've got someone's phone number, but I don't know the name attached and need it quick. I could rig up my room and quantum switch so it randomly picked and displayed a name on the wall. Then I could send someone in there with a phone book and ask them to look up that random name, and if it matches the phone number I've handed them on entering, to step outside and give me that name. They step in and the quantum event goes off and displays a truly randomly selected name out of my spreadsheet. Instantly the room is jumped up to tens of thousands of states in superposition as that person is looking up every single name at once. But a few moments later, only one of them steps out that door, and it's the one who had the right name for my phone number. To him, that was freakishly good luck, just happening to get the name that matched that phone number. That's a big application for quantum computers as a search method. It looks up every value, but only the state that was correct, which found the right entry, is shown. If you do it right, of course. The analogy I used wouldn't work in practice. Beyond macroscopic examples of quantum, like the cat in the box, not really being practically viable, a human is a very complex machine which themselves operate close enough to the quantum level that random stuff can probably spill out. Consider, one of our states is the guy in the room getting served the right name for the number. But with something as complex as human thinking, another one of those states would be getting the name right before that number, and seeing the desired number right below it. A second chance to be right, which is fine. But they might also accidentally think that was the number for their name and jot that down and exit. Ditto, someone might get a name that had a phone number one digit off, or transposed, and write that down and exit. Yet another might pat themselves down looking for their pen, miss it, and step out of the room to get a pen. And another might get served a name that matches their own, and step out to tell you about the funny coincidence. In quantum, anything which can happen has a probability of happening, and would have a state in that superposition. It might be incredibly tiny, but there's always a risk of error with a quantum computer, and it's going to be a lot higher with a giant and complex system like a human in a room. You only get to see one state, and you want a system where the right answer is 99.99999% likely to be the one you're shown. It is very unlikely that the guy is going to walk out of the room to inform you that his pen and paper underwent spontaneous quantum weirdness and turned into a slice of cheesecake. It's possible, but absurdly unlikely, so we are not concerned about that one. But it's quite likely they might make an error when looking at their name and comparing it to the desired phone number. The key thing, though, is that a quantum computer can do a search that no classic computer could possibly do, even a giant Matryoshka brain. A Matryoshka brain couldn't search the Library of Babel and find Shakespeare's Tempest in it. A quantum computer could. Similarly, there are certain types of calculations, like prime factoring, it can be very fast at. Any integer can be displayed as the product of various prime numbers. For instance, 15 can be factored into 3 times 5, 105 can be broken down to 3 times 5 times 7, and so on. I could pick a bunch of prime numbers and multiply them all together pretty quickly to produce some huge number, but it would take far longer for someone to take every prime number smaller than that number and try to factor it, as you go through all the possible combinations. It is not very hard to produce a number that even the biggest classic computer could not prime factor in less time than the lifespan of the universe. But the quantum computer can try each combination randomly and also simultaneously and pop out the answer almost right away. We use something like that for our encryption methods, because a system which can theoretically be broken but would require every computer we have to work at it for trillions of years is seen as safe enough, and that is why people talk a lot about quantum computers foiling our encryption methods. That's not exactly true, but it can beat that encryption method, so you have to use a different one that's safe against it. Quantum computers capable of doing that are a long way off. Quantum computers are also not magic wands. They do have limitations, and right now tons of them, because it is very hard to keep tons of atoms entangled with each other. And you want to be very careful extrapolating amazing abilities off the human in a room example I gave, because that was just for conceptual purposes. As I mentioned, there are a lot of problems using that. Even if you could set up that person in a box, and realistically you can't. But even if you could get that to work, you can't just take someone, toss them in that box, and tell them only to leave if they figure out the ultimate answer to life, the universe, and everything. You have to create a scenario where the correct answer is the most likely state for you to observe, and preferably so much more likely that the odds of observing a wrong one are nearly zero. I mentioned factoring a moment ago and gave the example of 3 times 5 equals 15. It was a huge deal a few years back when they managed to build a quantum computer that was able to do that simple factorization. Less mentioned was that they ran it thousands of times and it got the right answer 48% of the time. And Shor's algorithm, the one used for quantum factoring, holds that it's only going to get it right about half the time anyway. It was a huge technological accomplishment, and we've done better since, but it is important to keep in mind how far this technology has to go before it's useful even for niche applications. And the main school of thought is that there will always be tons of applications that classic computers remain better at. I don't want to oversimplify it, but in a nutshell, what quantum computers are good for is searching for needles in a haystack, pattern matching, and the kinds of problems that involve a lot of trial and error. And for all that the bits are atoms or photons, the device will tend to be bigger per qubit than a traditional computer's bit, because trying to keep a ton of atoms entangled to each other is a bit of a nightmare, and it's frankly amazing they've gotten up to 2000 qubits. It would be very easy to shrug and assume Moore's law will apply to quantum computers too, but we've talked before about the flaws of that kind of thinking and I won't repeat them now. It may well be that quantum computers with billions of qubits will emerge 40 or 50 years down the road, as such Moore's law doublings would imply, but we could easily bottleneck. When you start thinking about technology inevitably progressing on timetables, you're not doing science anymore, quite the opposite really. But we have no idea how big we will be able to make these and how long that will take, nor all the applications it might have. Plenty of people predicted enormous computers capable of billions of operations back when we were at this stage of classic computing, but we all know modern personal computing and the internet is nothing like what they were predicting. We all know what most people use the internet for, and I'm pretty sure Alan Turing never expected us to use computers to exchange pictures of cats with bad spelling and grammar pining away for cheeseburgers. So we don't know all the applications we will have for quantum computers as they get better, but we can expect to find plenty of applications for them besides the ones we've thought of so far. It's just too soon to tell, and they are a very promising technology. At the same time, they're not without their limitations. Hopefully, you've got a clearer picture of how they work now, and are in a good position to explore the topic in more depth. I always hate to say quantum computing is overhyped because it genuinely is groundbreaking technology with revolutionary uses, but at the same time, it's a topic cluttered with bad and superficial explanations. Hopefully I didn't just do the same and they make a bit more sense now. Okay, next week we will be returning to the Upward Bound series to look at skyhooks, devices able to help lift spacecraft into orbit. The week after that we will be looking at how you stay alive in space in an episode on life support, and we will clarify a lot of concepts and misconceptions about that which we see in science fiction, like the notion of life support being switched off and everyone instantly clutching their throats, gasping for air, or shivering from freezing cold. Make sure to subscribe to the channel for alerts when that and other episodes come out, and if you enjoyed this episode, please like it and share it with others. You can also help support the channel by following the links to the website or the channel's Patreon account listed in the episode description, and I also want to thank all the generous donors who help keep this channel going. Until next time, thanks for watching and have a great week.